So we talked about boosting and bagging and ensemble methods and drawing bootstrap samples. And so some of these ideas we can put together and apply them to decision trees in order to create an ensemble method based on decision trees. And one such ensemble method is random forests due to Breeman in 2001. And so this one is really, really popular and really, really powerful. Okay, so it's a good one to know. So k times you're going to repeat the following procedure, okay, where k is a parameter that you'll specify. You'll draw a bootstrap sample from the data set and then train a decision tree on that bootstrap sample as follows. So until the tree is some maximum size that is usually set pretty conservatively, you'll choose a leaf node, iterate over all the leaf nodes, and for each leaf node, select m attributes at random out of the p that are available. Okay, so you're not going to use all the, you're not going to consider all the attributes when you're deciding how to split a node. You're just going to select m at random and consider among those. Okay, and then pick the best attribute or split of the attribute as usual using entropy or other methods, and we'll talk about one more. Okay, so now you have a tree that only involves m of the attributes, and it was derived from only part of the data set. Okay, so now you measure the out-of-bag error. So what's the out-of-bag error? Well, when you draw a bootstrap sample, remember that you might get duplicates, right? So you have a data set of size n, you're going to draw a bootstrap sample also of size n. But whenever you get a duplicate, that means that some other data item was left out of the sample. Okay, so take all those data items that were left out of the sample, and that becomes your test set. All right, so now evaluate the error on that test set and use this for, you can use this for various purposes. Okay, you don't necessarily need to use it to make decisions as part of the algorithm, but it's computed on the fly as part of the algorithm for various other purposes. Okay, so you can do this to estimate the strength, which is the inverse of the error rate. You can do this to measure the correlation between random trees, right? So each one of these is sort of a different tree using different, potentially different attributes and a different subset of the data. But you can imagine that just by chance you might get a bunch of trees that all do the exact same thing and make all the same decisions, right? This would lower the power, lower the strength of the overall ensemble classifier, and so you don't want that. And so this gives you a running measure of how correlated things are, okay? And it also gives you a measure of variable importance, which we'll talk about in the next slide. Okay, so finally at the end of this you have k trees that are hopefully more or less independent, and now you can classify data points coming in by just a majority vote among them. All right. So this notion of variable importance. So one of the weaknesses of ensemble methods that we mentioned are perhaps the interpretability of them, right? So a single decision tree makes a lot of sense. If I have a whole set of decision trees all sort of working in concert, it's a little less clear what's going on. And so if you're actually trying to use these models to gain some insight about the domain, that may be difficult with a random forest. All you get is sort of the answers out, and they have high accuracy, but you don't really know why it works. Okay, so variable importance is a hedge against this. So the idea is that you'll, as an output of running this algorithm, you'll get a measure of how important to the accuracy the various attributes were. Or I'm using variable and attribute interchangeably. Okay, so how do you measure this? Well, as you're training each tree, you do this permutation experiment, and we've seen this before, at least I think we have. So you'll scramble the values of that attribute, and what you'd expect is that once you scramble these, the accuracy, the error rate, it may change. Okay, and if it's an important attribute, then it'll change a lot, and if it's not a very important attribute, then it doesn't change very much. And so that's the idea. So if you scramble this and the error rate does not change very much, then it must not have been an attribute that was heavily used in the decision tree. Okay. All right, so you measure the error increase after permuting these values, and you can plot for all the attributes in the data set which ones came out to be most important by aggregating these across all the trees. Okay, and so this helps with interpretability of the overall random forest because you get a sense of which ones are really helping to make all the decisions. All right, and so in some applications, in particular, a few places mentioned that medical applications need to eventually get down to root causes rather than sort of doing fire and forget treatments. All right, fine. So one other difference is the Gini coefficient is often used, and this actually comes up not just in random forest, it comes up in variations on decision tree algorithms. And so we talked about entropy as a measure of impurity when you're making a decision on each node, right? You need to decide which attribute to split on that'll give you the most reduction in uncertainty, okay? And so you're looking for choices that'll give you very pure choices to the left and very pure choices to the right, right? Where if I select female and male, then I get 100% of the records when I go down the female branch all survive in the Titanic data set. Okay, so somewhere down the decision tree, this may turn out to be the case, in which case that would be a strong indication to use the gender attribute to make the split. Okay, and so we measured this we counted up this measure of intuitive notion of impurity using entropy. Another calculation of the intuitive notion of impurity is the Gini coefficient. Okay, and so this looks like this. And so if you think about what this is doing, right, you can think about how this behaves. We're not necessarily going to derive this, and there's actually varying notions of how to compute the Gini coefficient in general. But if you think about how this is behaving, that if you have probability 0.5, then square that and it'll be plus 0.5 on the other side. Say we have a binary class, so just survived and not survived. Then this will be 0.25 plus 0.25, which is 0.5. Okay. But if you have 0.1 squared plus 0.9 squared, well, that's going to be a lot smaller. Okay. So 1 minus that will be much bigger. Okay. And this makes sense because if 90% of the values are the same, or you know, if 90% of the values are one value and only 10% of the other, then this attribute is more pure than something that is evenly split. And so you still got this function that's ranging from 0 to 1, capturing some notion of purity. And this has the same properties that has that same property as entropy did. Okay. All right, so now you know both of those methods for measuring this impurity, and you'll see both of them in practice and decision trees and the libraries that implement them. All right, so just a couple of comments about these random forests. You know, one is this is easy to parallelize, right? All that requires is being able to take a random bootstrap sample in parallel, which is usually easy for most data sets. If the data sets are very, very large, it can be expensive to take random samples, but it's still a lot cheaper than training models sequentially. Okay, and so other than that, the training of the trees can all happen in parallel, and so this scales out really, really well. The other nice feature of this is because you're selecting those M attributes at random, where M is oftentimes a lot less than P. You know, you're only selecting a few of the attributes, which makes sense, right? Because if you're going to have a whole bunch of trees vote, well, you're going to make sure that every attribute in the whole data set will be represented enough. You don't necessarily need to have them represented in every single tree. Well, this is nice because it sort of scales to very large numbers of attributes quite well. All right. And then it has these other side effects of being able to generate on-the-fly estimates of its own accuracy and variable importance and so on. Okay. Great. And so just to summarize this, going back to this framework of representation, evaluation, and optimization. You know, the representation here is trees or sets of trees, where the majority vote determines the actual classification. The evaluation of these things has to do with just error rates and accuracy, although we talked about some of the other measures that you might use. And then random forest, we have this out-of-bag error, which is same thing as accuracy, but it's defining where you get the test set from, right? It's left. It falls out naturally from the fact that you're taking bootstrap samples. All right, so you don't have to make a separate decision about cross-validation and so on. Although I should say you should still. This is sort of independent of cross-validation. This is, this out-of-bag error is generated on your training set. You should still beforehand, before you even walk up to the table, consider how you're going to do cross-validation or how you're going to split your training set into test and training. All right. And then finally, optimization. It's not so much an optimization as in we have a naive algorithm and we improved it with some optimization, but we do have this information gain Gini index approach to constructively build trees that have good predictive power, right? So we could take, we say random forest, but it's not truly random in the sense that we're just building random trees, right? Those wouldn't perform very well. We do better than random by making smart decisions about how to split the nodes, which attributes use to split. Okay.